Okay, class, so welcome back. So we're going to be continuing with sequences today. So remember, we defined these at the end of the last lecture. You can quickly define these as just functions from n to r. Okay, so in other words, they're ordered sequences where we have f of 1, f of 2, f of 3, and so on. And usually we denote this by x1, x2, x3, where the xi are real numbers. Okay? So the most important definition for a sequence is the following. So xn, a sequence, and I'll write this now, but I'll probably leave it out for the rest of the lecture or for the class. Okay, so whenever I write this, I always mean indexed by the naturals. Is said to converge to x in R if, so maybe this is important enough that I'll try to make its own little line. For every epsilon greater than 0, there exists some n, which will depend on epsilon in the natural numbers, so that for all n bigger than or equal to n epsilon, we have that the absolute value of xn minus x is less than epsilon. So, in other words, if you give me a little wiggle room, so for every amount of wiggle room, you can imagine you're kind of conducting an experiment. I give you a sequence, you're trying to say where it converges, but of course you don't have infinite accuracy in this experiment. So maybe you have epsilon accuracy. You can kind of tell where everything is up to epsilon. Then as far as you can tell, the xn and the x appear to be the exact same thing, right? Because they're less than epsilon apart. And then it converges if kind of you can do this for any amount of epsilon or any small epsilon. So for any wiggle room, if you go far enough in the sequence, the terms are never farther from the target than this wiggle, okay? Than the wiggle. Okay, so what this means, well, I'll just draw the kind of real line picture now. We have x in R. We don't really have any idea what the numbers are doing at first, okay, or what the sequence is doing, but we know that if we give you any little epsilon, eventually we're all inside this here, okay? And this happens for any little interval around. And of course, this is why we take the absolute value. I don't know whether the sequence is kind of less than x or greater than x, but it's just somewhere around there. Or very close to there. So let's do some examples. Some of them we've kind of seen before. So the first is that the sequence 1 over n goes to 0, okay? So this is similar to the statement that the nested intervals 0 to 1 over n have intersection 0. And this, we've seen before that there's kind of a similarity between sequences and looking at nested intervals. So to prove this, with this new definition of convergence, so if epsilon greater than 0 is given, and usually I'll just write let epsilon greater than 0 and then start the proof. We need to find an n in n so that 1 over n is less than epsilon for all n bigger than or equal to n. Okay? I guess I should have wrote here 1 over n minus 0. I mean, it's just something to keep, kind of track of. And so this will turn out to follow essentially from the Archimedean principle. So let me just put this here. So we want to have 1 over n less than epsilon. This is the same as 1 over epsilon being less than n. You want this to always be true for sufficiently large n. Well, this is greater than 0. And what this means is, by the Archimedean property, there is an n in n so that 1 over epsilon is less than n. Therefore, this is if and only if 1 over n is less than epsilon. And the same thing happens for all n bigger than n, right? So, and the same is true for all n greater than or equal to n, okay? So similarly, notice it's a little stronger than saying something we had shown before, which was that the infimum of the set 1 over n, I should have not put the sequence there, just 1 over n in n was 0. We saw the Archimedean property implied this. This is saying something a little stronger, because not only is the infimum 0, but if you go far enough out, all the terms are 0. Okay? Okay, so here's kind of the first key fact about these limits. Okay, so here's, I'll say it as a theorem. Limits of sequences are unique. Right? So notice, we'll see soon that, of course, a sequence does not have to converge to any number. But if it does converge to a number, then it can't converge to anything else. Okay? And, if you want to prove something about limits of sequences, you better have, it's nice to have unique ones. Okay? So how do we do this? Well, suppose we have xn, which converges to x and converges to x prime. Okay, so the same sequence converges to two different things. What we'd like to show is that, so we want to show that the distance between x and x prime is 0. Okay? This will imply that x equals x prime. So what do we know? Since x then converges, for any epsilon, let me say over 2, which is greater than 0. Okay, so you can do this for any epsilon. It's just convenient to take that epsilon and divide it by 2. Okay, just to make it look a little prettier later. So what do I know? I know that there exists some n1 in n, so that xn minus x is less than epsilon over 2 for all n bigger than or equal to n1. And I also know that there exists some n2 in n, so that xn minus x is less than, x prime is less than epsilon over 2, again, for all n bigger than n2. So notice I can't assume anything about what n1 and n2 are, because I only know that they converge. I have no idea kind of that they converge at the same rate to x and x prime. So it might take, it might take, this n2 might be much larger to get with an epsilon over 2 than this n1. That's fine, okay? What you know then is that if you go further than both, so if you take an n which is greater than or equal to the max of these two, so just the larger of the two, well, what we know is that xn minus x is less than epsilon over 2, and xn minus x prime is less than epsilon over 2. So here's the picture. We have x prime, and we know that there's xn sitting in here, so that this distance is less than epsilon over 2. Sorry, the handwriting's getting small, and same here. So what we want to conclude is that we want to say that this implies that x minus x prime is less than epsilon. Okay, and notice we would be done if we could do this, right? Because since epsilon was completely arbitrary, so it would be less than epsilon for, the distance would be less than epsilon for any epsilon. This would imply the distance is 0 and x equals x prime. Okay, so how do we get to this conclusion? Well, it's kind of a classic trick, which if you never have seen it, or haven't been comfortable using it, it seems crazy or to come out of nowhere. But it's actually just well, it certainly comes up a lot, and it's quite natural. Okay, so you write x minus x prime. You're trying to figure this out. You don't know anything about it, except that you know that both of these are close to xn. So you just put in an xn. So you have x minus xn plus xn minus x prime. So you just add a 0, but of course but it's in terms of xn minus xn, or xn, yeah, minus xn plus xn. And then by triangle inequality, you know that this is less than or equal to x minus xn plus xn minus x, which is less than epsilon over 2 plus epsilon over 2, and that's less than epsilon. Okay, so we're happy. So this is kind of, it's a good trick to know in real life also, not just math. So if you're ever trying to figure out the distance, say between two cities, two destinations, what this is saying is you can get some estimates for what it is if you know the distance between each city and a third place. So, maybe you're trying to figure out the distance between Chicago and London, okay? You don't know it, but you know the distance between Chicago and New York and the distance between New York and London. Then you can't figure out exactly the distance from Chicago to London, but it gives you some bounds as to what it can be, okay? Which can be, comes up in real life if you start thinking about it. All right, so let me give you a lemma, which is essentially just a restating of what it means to converge, but I'm going to kind of go between these two different definitions without thinking about it, so I thought I'd write it down. So we take a sequence and x in R. So then the following are equivalent. And I wasn't actually sure if I'd used this shorthand before, but I'll just put it here. Okay. So the first is, well, xn converges to x. The second is for any epsilon greater than 0. There's some n and n, so that, for all n bigger than n, xn minus x is less than epsilon. So that's just, xn minus x, sorry. So that's just the definition of convergence. And then again, for any epsilon greater than 0, there's some n and n, so that for all n bigger than or equal to n, x minus epsilon is less than xn, which is less than x plus epsilon. Okay? And the proof is just, well, if you write xn minus x being less than epsilon, this is equivalent to negative epsilon being less than xn minus x less than epsilon, and adding x to every side, this is the same as x minus epsilon less than xn less than x plus epsilon. Okay? So in some cases, when you're doing proofs, it's kind of natural to use absolute value, and then sometimes it's natural to use these inequalities, and I'll just go kind of back and forth between them. Okay? So let me tell you kind of a key but unfortunate remark, which basically implies that finding limits can be quite tricky. Okay, so the problem is, or just, what life is that the definition of limit doesn't give us a method to discover what the limit is. Or maybe I'll do sad face. Okay? So what this is saying is I'm giving you a sequence, right? I have a sequence xn. I know the definition of convergence. I know that if it converges to something, it's unique and everything's wonderful. But the thing is, how do I find this x that I have to search out, right? I mean, I've given you the sequence. I know the definition of xn converges to x, but this doesn't help at all actually find the x. So it becomes kind of difficult to verify in general. If I give you a random sequence and I ask, does it converge? Well, you have to check all the, there's no better way to check the real numbers. So we have to just come up with kind of more techniques which will let us actually figure out what the correct choice of x should be. And then you still have to figure out, how to prove that that's actually the limit of the sequence. Okay? So let me give you an example which will lead to kind of a useful, or probably the most useful method. Okay. So we want to show that 1 over n squared plus 1 converges to 0. Okay? So let's do this. So we're going to let epsilon be larger than 0. And we need to find an n in n so that, big N, for all n bigger than n, 1 over n squared plus 1 is less than epsilon. So n squared plus 1 looks complicated, right? In the sense that it might be kind of difficult to try to solve for n, okay? So what you want to do is to simplify your life and reduce to something that we already know, okay? And here we can do this, right? Because 1 over n squared plus 1 is less than or equal to 1 over n squared, because the denominator is now smaller, and this is less than 1 over n, since again the denominator is smaller. And that's good, right? Because this we know what to do with, okay? So therefore, if we let n and n, so that 1 over n is less than epsilon, by the Archimedean property, as we did before, then the same n works, right? So for any n bigger than n, 1 over n squared plus 1 is less than 1 over n, which is less than epsilon, okay? Which is just what we want. Notice this already gets a little bit tricky if I had taken 1 over n squared, minus 5, right? Now, of course, this so I have to be a little bit careful, but I think that's okay. I'm never dividing by 0, okay? But I won't always be able to say that this is less than 1 over n, right? So I have to, do some more algebra at some points if the numbers don't work out as nice. Okay, so let's do another example, which is kind of along these lines. We're going to have 3 times m plus 2 over n plus 1 converges to 3, okay? So how do you show this? Again, it's lucky that we kind of know what the answer should be. All right, so again, given an epsilon greater than 0, let's just write down, since this is a little different, what we actually need to show. So we need to show that 3n plus 2 over n plus 1 minus 3 is less than epsilon, again, for some n bigger than n that we find, okay? So let's, this obviously forces us to do some algebra here. So let's do it. So we know 3n plus 2 over n plus 1 minus 3, so we can write this as 3 times n plus 1 over n plus 1. So we get 3n minus 3n plus 2 minus 3, so I believe we get minus 1 over n plus 1. Okay, and then I'll just stick on the absolute values. So this is exactly the same as 1 over n plus 1. This is less than 1 over n. So again, the same n works. Oh, same large n works. So let me just put in what's going to be a lecture problem. Okay, which is come up with a sequence that does not converge. Okay, and it's actually slightly better if you come up with a bunch of examples that don't converge for different reasons. Okay? So I will let you think about that. Okay, so I want to now start kind of putting this in these last couple of examples in a more general framework. Okay, so here is kind of the general idea for showing something converges using these comparison theorems. So the theorem is let an converge to 0. So you can think this is supposed to generalize or be 1 over n in the past examples. For simplicity, I'm going to assume that an is greater than or equal to 0 and x in R. So if there exists a C which is a positive, and there exists some m in n, so that xn minus x, so this is some different sequence, is less than or equal to CAN, for all n bigger than or equal to m, then xn goes to x. Okay? So you can imagine what, instead of doing something like epsilon going to, for any arbitrary epsilon, finding some n, what we're doing is bounding the distance between our sequence and its limit by a different sequence which converges to 0. And then what we're also allowed to do here is also multiply by an arbitrary real number. It turns out it's pretty easy to check that if a sequence goes to 0, then you multiply that sequence by a real number and it still goes to 0. Okay. So let me give you the proof. As usual, we just have to show, we start with epsilon being bigger than 0. And now what do we know? Well, we're using this assumption here. So we have an converging to 0. What does this mean? Well, it tells you that there exists some n in n, so that an, I guess I'm assuming I don't even need to write absolute value, is less than epsilon for all n greater than or equal to n. And since I'm assuming that I'm going to have some bound in terms of some constant, it's convenient here to just put epsilon over c. Okay? So we will see that this will ensure that we have a nice epsilon term in the end instead of a c epsilon. Okay? So what does this now imply? Well, I know that xn minus x is less than or equal to CAN for all n bigger than or equal to m. And this an is less than epsilon over c for all n bigger than or equal to n. So for all n which is greater than or equal to the max, of big N and big M, I get that xn minus x has to be bigger than or equal to CAN. And by this is less than c times epsilon over c, which is less than epsilon. Okay? And then again, since epsilon is arbitrary, this means, this means that the sequence xn converges to x. Okay, so let me do an example which will really kind of come from homework 4. Okay? So the example is if 0 is less than b is less than 1, so b is some in the open interval 0, 1, then b to the n approaches 0. Okay? So what this means, we haven't really touched on exponents yet, but this is just b times b times b n times. Okay? So what you can have in mind is b is a half, so you get this sequence, a half, a fourth, an eighth, a 16th, and so on. Okay? So again, we want to prove something about b to the n. And we don't really know much about exponents at this point, so we'd like to relate it to something that we already know. Okay? So let's just do some arithmetic here. So b being between 0 and 1 means that 1 has to be less than 1 over b. So in particular, 1 over b minus 1 is greater than 0. And now I'm doing something which will look excessively complicated, but I promise it is for a good cause. Okay, so I'll write b is equal to 1 over 1 over b, which is 1 over 1 plus 1 over b minus 1, which is 1 over 1 plus a, where a is equal to 1 over b minus 1. Okay? And all I care about a is that it has to be greater than 0 by assumption. Okay? So then b to the n is just 1 over 1 plus a to the n, where, as we said, a is greater than 0. And now, hopefully, this is looking somewhat familiar. Right? By the last homework, we know that 1 plus a to the n is greater than or equal to 1 plus na when a is greater than or equal to minus 1. So in particular, when a is greater than 0. Okay? So now, let's use this homework. Okay? So we have this. So what this means is that we have 0, which is less than b to the n. I'll just write this out again. This is now less than or equal to 1 over 1 plus na, because we've made the numerator smaller. We've made the denominator smaller. Then this is less than or equal to 1 over na, again. But we know something about 1 over na, right? This was just, so a was some positive number, so it's just the sequence 1 over n times some positive number. So this goes to 0, so we're done. Okay? By the previous theorem. I mean, in this specific case, you can go through and do the epsilon argument again, but we just proved the last theorem so that we can just say, well, if this goes to 0, we're done and we are happy. So, let's use it and be happy. Okay, so this kind of Bernoulli inequality, which I guess I never gave it a name on the homework, but it's this, okay? So it's very useful in general. So it's kind of a good trick to have in mind or to keep in your back pocket. So what it does is it turns powers or exponents, which are generally hard, into sums, which are generally easier. Okay? Right, so now let me kind of do our last topic for today, which is kind of our goal is going to be give conditions on sequences which ensure convergence. So we have seen a little bit of this, right, in some of the theorems that we did today. But on the other hand, they were slightly self-referential, right? So if I give you kind of one of the main theorems that we had seen about how to show a sequence converges, well, it's true that the conclusion was that a sequence converged, but we had to assume that we started with a sequence that already converged to 0. So it's reasonable to ask, well, what you really want is conditions on a sequence which guarantee it converges without any reference to any other sequence, right? Just conditions that you can put on the sequence alone. So we won't do this today, but it's coming, okay? But first, I'm just going to give you kind of a useful definition, and then we'll show that if a sequence converges, it does satisfy this definition, okay? So it's just exactly similar to a subset, right? So a sequence Xn is bounded. Essentially, if the corresponding set is bounded, but I'll write it out. So if there exists some alpha in R, so that Xn absolute value is less than or equal to alpha for all n in n. Okay? So a key fact, which I'll write as a lemma maybe, this detects divergence So in other words, the lemma is that convergent sequences are bounded. Okay, and this turns out to be reasonably simple. Okay, so what happens here? I have a sequence, which I don't know what it does for the great majority, for a reasonable time. But since it converges to X, I know at some point it has to live within, say, X plus 1 and X minus 1. Okay? So at some point, in its life, it decides to live only in this interval, and then it does that for the rest of its time. Okay? So then the bound, so the upper bound, or the upper / lower bounds, are given by, well, there's kind of two possibilities. Okay, so either what can happen is it reaches its upper bound here, okay, at some point before it's forced to live into, in the X minus 1, X plus 1, that looks like an I, interval, okay? So, in particular, if you give me, I'll choose let n in n, so that xn minus x is less than 1 for all n bigger than n. So one of the upper and lower bounds could be just realized, so the upper / lower bound might be one of the previous values. So one of the values x1, x2, up through xn minus 1. Okay? So that can happen. Like, the sequence can jump around terribly before ever becoming convergent. So, x4 might be, x might be 0, but, as far as you can tell, the 10th term of the sequence was a googol. Okay? And that's the upper bound. But there's only a finite number of elements on this list. You can just detect by taking the minimum or the maximum, what the better bound is going to be. So the other possibility is a sequence which perhaps looks like this. Here's x, and none of the earlier terms in the sequence are upper or lower bounds. Okay, so otherwise, the sequence is bounded, say has an upper bound by x plus 1. Okay? Because you've exactly kind of ensured that since it converges, it has to live within the x minus 1, x plus 1 interval. Okay, so that detects convergence of sequences. So you can think I've already given you one example for the previous lecture problem. Right? If I look at the sequence 1, 2, 3, and so on, this has to be a divergent sequence since it's not bounded. So maybe maybe now if you've thought about the first lecture problem, now come up with a sequence which is bounded example, but divergent. Okay? So come up with a sequence which is bounded, so you can't just use this trick, but is still divergent. Okay, so I think that was kind of a lot today, so I think I'll say thanks.